So if you don't know where Glasgow is, it's towards the northern part of UK, and it's a city in Scotland. So it's very near to the capital, Edinburgh. And it has got a very strong information retrieval group in the university. And I'm a part of that as well, because my primary research focus is on information retrieval. But recently I've been interested in explainable AI as well. So I'm very happy to share some of my own thoughts about explainable AI in general. So this presentation of mine, let me see if I can change my slides. Okay. Oops. Oh, yeah, it works. Okay. So I won't be giving a technical description of the algorithms as such, which my students will kind of cover, very, very specific details of two specific algorithms, L2X and Shapley to be more specific. So I'll be giving more of an overview about explainability in general, as it applies to AI and different domains of AI, so as to say, because, you could have classification, you could have text classification versus image classification, you could have knowledge-based completion and, other tasks like question answering. So how does explainability fit within all these tasks? So that's something that we'll look at. And so we'll start the presentation with a very basic motivation of why do we need explanations at all in the first place? So we're talking about the evolution of AI systems from feature-driven to data-driven ones, the ones that we call deep learning nowadays. So we'll say, why explainability is important in these kind of models. And then we'll be talking briefly about the issues of trust that's associated with explainability as well. So one of the main, motivations of explainability, seeks to build up user trust in these models. So we'll be talking briefly about that as well. And then we'll be talking about the types of explanations that you need for different types of tasks. Like, obviously, what explanation units, will serve for image classification won't be the same for text classification. And it'll be different for knowledge-based completion and so on and so forth. So we'll be seeing examples of explanations for each of these different tasks. And then, I'll be briefly talking about, not at very depth in details, but, very, very abstract overview of how typically does an explanation mechanism work. And, we'll be having a case study of Lime. Again, I won't be delving very deep into Lime, but we'll be trying to throw you the concepts, which anyway, I think, if you grasp the concepts in this session, then I think it'll be easier for you to grasp some of the discussions about L2X and Lime that will be given by my students later on. And then, I'll be sharing my thoughts about, where can we go from here? So the explanation state of the art nowadays, what we have, it's still the tip of the iceberg, right? So it's very basic. But thinking about the future in the coming 20 or 30 years, so where do we envision to carry this work forward about explanations? And I'll be sharing some of my own thoughts about it. And then, one of the useful aspects of explanations in AI is that, you could possibly try to apply it for societal benefits as well, like building fair AI systems. So I'm talking very briefly about that before concluding my talk. So without any further delay, let's try to kind of see, what's the basic motivation behind the explanations. So here's a very simple example, right? So I think if you have watched Rick and Morty, so you already know that Rick is a scientist who talks in very scientifically rich jargon, who uses very rich scientific jargons to explain something. So you can imagine that Rick in this case is an AI system, which uses very complex functions that typical users or non-technical users may not understand, right? So imagine that his grandson is asking a simple question like, which movie should I watch? And, so if it's a simple answer, right? So you have to say that, okay, so maybe you should watch this movie because in the last week, we have watched those two movies and then you like them. So maybe, I think that you should like this as well. But instead of coming up with this explanation, if the AI system or if Rick in this case says that, okay, so what am I doing exactly at the back end? Like I have stacked layers of convolutional networks over which I have a feed-forward layer and a TAN-H or a softmax activation function to classify which movie you should watch, then this is something that doesn't serve as an explanation, right? So this is the very motivation that, when you deploy AI systems into production. So the users who will be using them, they could be doctors, they could be, I don't know, any professionals that could be consulting the systems to get a decision. So we have to build some kind of trust, and you need to be providing answers that are understandable by the people from those domains. So it should be explained in terms of concepts, or very simple units, data units for those domains, right? So if it's images, then maybe you should show regions of images and then say that, okay, so why is this classification working that way? So we'll be showing some examples of those again. Okay, so as I was talking about that, so why do we need this jump, or why do we? So there has been a jump from the feature-driven models to data-driven models, and we need the explanations because of this jump. Because previously, if you think about feature-based systems, so it was easy for us, or for humans, to kind of maneuver the features and then kind of come at an answer that, okay, so I think that this model is not working because it's not having that feature. So it was really the features that was kind of determining the accuracy of the models, right? So just to give an example, so why do we need to jump in the first place from feature-driven to data-driven models? Because so in feature-driven models, imagine that you want to build a classifier for some domain. So you need to hire domain experts who kind of know what are the discriminative features that particularly works for that domain. And then you build up your system using those features. But then if you need to build up another AI system or another model for a different domain, then you need to hire a different set of experts to come up with the features again. So you need to kind of reinvent the wheel every time, if you want to transfer knowledge from domain to domain, right? But this is not clearly a scalable solution. So this is not the way we humans learn, right? So we are not being, so let's take an example, right? So let's say that you want to build an image classifier system that can distinguish between the images of dogs and cats. So what are the features that we should typically use? I mean, consider feature-based models first. So maybe the presence of whiskers, or I don't know, the presence of long ears in dogs. So these could be, or the size of the teeth, or I don't know. So maybe any other, maybe something else. Maybe the length of the hair or something. So these typically will be the features that you will typically use to classify or distinguish between cats and dogs. But this is not the way we humans learn. So how we learn is that our parents never tell us that, okay, so you should look for that specific feature, when, so identifying between a cat and a dog. We don't do that. Our parents, when we are young, we are told examples of classes, right? So we are told that, okay, so that's a cat and that's a dog. And we build some kind of an abstraction in our own head, right? So this is called data-driven learning. So you are not really given a set of features, but over time, with many examples, you will kind of build, some abstract notions of features inside your own head. And this actually helps. Why does it help? Because if you build the abstractions, then you are not really tied down to the particular domain for which you want to apply the classification algorithm, right? So, if our parents have said, okay, so this is a cat and this is a dog, and this is a kitten and this is a puppy. So the thing is, you build all these abstractions parallel, right? And then, it's easy to transfer the knowledge. So, if you're asked that what's a cat and what's a dog, then you could use that abstraction that you built between cats and dogs. And if you are asked, what's a kitten and what's a puppy, or what's a kitten and what's a cat, then you could use different abstractions to kind of classify between them, right? So this is the whole motivation, why we want to jump from feature-driven to data-driven models, because we are not really tied down to a particular application domain, where we need to be kind of maneuvering or engineering the features that we want to build up. So this advantage of the data-driven models is that you can easily transfer your knowledge from one domain to the other domain. So how do we do? Like, as I said, we humans, we build some kind of an abstraction about the data. So all we are shown is examples, and we build some kind of abstractions depending on the labels of those data. This is the exact same thing that we do for data-driven ones, for deep learning models, to be more precise. But the fact is that our human brains are somehow better in terms of grasping or getting hold of the abstractions with very few examples. But unfortunately, for deep learning systems, as of today, we need maybe thousands or tens of thousands of examples to actually build up the abstractions. The way we build the abstractions is like layers of neural networks. So they could be like one-dimensional convolution, or some kind of sequence model like with LSTMs or recurrent neural networks for text, or it could be 2D convolutions, because in images it matters. Not only you have linear dependence between the left and the right, but you could also have dependence between the top and the bottom regions of the images. So it turns out that if you apply a two-dimensional convolution, that typically helps to kind of abstract out the features from images. So this is what we do, right? So that's the motivation from getting from feature-based models to data-driven models. But this means that so on one hand, we increase the scalability, or we increase the production, the time it takes to build an AI system for a new task. But it also means that we have less control over how things work. I mean, if it was a feature-based system, we humans could, leave out some features or include some features that we think are most suitable. Like, I'll give you an example. So let's imagine that you want to build a classifier for you feed in human faces, images of human faces, and then you say, okay, so what's the likelihood that this person is a criminal or not? I mean, this is a very kind of, I don't know, controversial kind of AI system, but it has been put in practice. I mean, there are systems which tries to do that. But obviously, if you want to build a fair and just system, you typically leave out attributes like skin color, from the way this classifier works, because it would be really unfair to land up with cognitive biases like brown people are more, or black people are more prone to be criminals. I mean, it's a complete disaster, if you have this kind of a classifier. But with feature-based systems, you could leave these features out. But with data-driven ones, you don't have any control, right? So, you just have labeled examples. And if you feed in the labeled examples, then it might happen that the abstraction it builds, or the AI system builds inside, maybe, the skin color emerges out as one of the dominant features. So which you can't really control, right? So that's why we need explanations, right? So we need to be kind of understanding ourselves, that how is the model working? I mean, the model, you feed in some data and you get some predictions, that's fine. But then we want to be knowing, what are the abstract representations that the model is building inside, so that it gives us, some kind of a control, right? Of understanding how it works first, and then kind of controlling the way it may work. So that's the whole, purpose of explanations. Okay, and also for trust issues, right? So as I said, so for a different domain, or very, very time or very sensitive domain, like say, for example, healthcare, if you're building a system, and if the system is coming up with some predictions, so it might be the case that the experts in those domains, like say doctors or nurses, they're not really prepared initially to believe your results, right? So you'll be asking a lot of questions, like, okay, so let's imagine that you are feeding in some patient report, and it comes up with an answer of what likely disease the patient could have. So doctors and nurses, they will have their own way of figuring out things, right? And if a system, if you build an AI system and deploy it, and then it comes up with a prediction, they'll be wanting to know why. I mean, so okay, I understand that you are saying maybe it's a flu, but then how did you arrive at your decision? So I think that in those cases, if the system doesn't provide a clear answer to these questions, then these users or that's experts in these domains is very likely not to trust your system. I mean, they will typically say that, okay, so maybe it's by coincidence or by something else that it just comes up with that prediction, and I don't really believe your system. And what they will typically do is that they will try to play around with that system. So they will try to maybe insert something that they feel like, I mean, they will be having these notions in their head, right? So okay, so these are the symptoms, and if I add this thing, then probably it's not a flu. I mean, if you have all the symptoms like, I don't know, sneezing and coughing, but you don't have fever, then maybe it's not a flu. I don't know. So it's just an example that I'm making up. But then they'll be very happy about playing with the system, and it's very easy for the system to crack. I mean, if you're not really sure how the system works, then probably if you turn off or if you add some feature, then very likely the system is going to be answering something that's not going to be pleasing them or not going to be consistent with their own understanding about the domain itself. So that's a risk. So that's why you need to be coming up with answers to be convincing them in the first place, right? So this is the notion of trust that if you deploy systems for new tasks or for critical tasks, explanations can help build up trust. So there are two aspects to it. One is trusting a prediction, and the one is trusting a model, which I'll be talking about. So when it comes about trusting a prediction, so as I said, you'll be you want to explain one single instance, right? So one single instance of data you throw into the classifier or to the prediction system or to any AI system, you get some output, right? So it could be a class label, it could be a continuous value, it could be, I don't know, an answer. Or it could be a machine translation, if you are working on machine translation. But you need to apply, you need to explain that particular instance, right? So we are not concerned about explaining the whole model of how it works, but we just want to explain one particular instance. And any explanation of that sort, has to go back to that instance and then say, okay, so these are the basic units. So if it's images, then you should say, okay, so since this part of the image or the presence of this object in the image, that's what makes me believe this classifier or this class that I'm predicting, right? So that's the prediction. That's the instance level predictions, and then you could also have model level explanations, right? So where you are not really bothered about one single instance, but as a whole, you want to build up maybe. So if you are deploying, I don't know, a disease classification system, so maybe the doctors will have some of their own test cases in their mind, right? So they will typically have some I don't know, some prototypes of tests that they'll be interested to throw into the system and then see how it works. I mean, that's how they test young doctors or something. So that's like seeing the whole model, how it behaves on many different inputs. So keep in mind that there are two aspects to explanations. So you'll see that there is a very direct way of obtaining the prediction level explanations or obtaining the instance level predictions or the instance level explanations, but there is no obvious way of getting the model level explanations. I mean, that's more difficult. I mean, people would typically apply the instance level explanations and then use a set of that to explain the model level, but I don't think that's the best way of doing it, because explaining model level, coming up with model level explanations is very difficult, because you don't nearly know all the instances that you could provide as inputs to the system. It depends on some distribution, right? So maybe you leave something out. Maybe it's very easy for you to miss something out. So people who try to do the instance level predictions to explain the whole model, but that's not it's not a very clear way of how to obtain model level explanations. Okay, so now I think we can provide some examples that I was talking about initially. So explanations, as I said, it's for different domains. Your explanation mechanisms or your explanation outputs should be different. So, like, say for example, I also gave this example, right? That you feed in some document which contains all the symptoms about a disease, and then you want to classify that what disease that is. So an explanation system in that case, it could try to say that, okay, so since I believe that sneeze and headache, they have played a positive part into my inferring that it's a flu. So if the system comes up with the prediction flu, it also will or can come up with weights saying that these were the positive factors that made me believe that this is a document about flu, or the disease here is most likely a flu. And since it's a fact, so in this case, it's a contradiction, right? So there is no fatigue, but then the model says that no fatigue, probably it's a reason for it being a flu, but maybe it's not. But I don't know. So you could get explanations like this, right? So, and then take another example, like so this example in figure 2. So this is an example of email classification. So you are given emails, and then I think that the two classes that it tries to predict are Christianity and atheism. So if you're trying to classify between them, and so it makes sense that if your model is emphasizing more on words such as God and mean, anyone, so maybe it makes sense that any terms related to God, probably it makes sense that it's talking about atheism or Christianity. But if the model is kind of putting more emphasis on words like posting and host, so these are all words that come from the email body or the email headers. So if it's putting more emphasis on the email headers, then probably it's not a good classifier, right? So maybe it's coming up with the correct prediction, but then the way it's arriving at the results, it's questionable. So that gives the user, a kind of a tool to kind of check that whether the model is kind of taking into account the features that really a human should have taken into account. So whether the abstractions of the model builds up, it is consistent with the human notions of the way we perceive about those data. And for images, it could be segments from the images that you could highlight and then block the rest of the image and then say that, okay, so in this case, you get an image where you have got many different things. You have got a dog wearing a hat. And it's not really a dog, it's a human, but then the dog's face is kind of juxtaposed on the human's face. So a human is playing the guitar. It's an acoustic guitar, but then I think for this example, the system comes up with a prediction that it's an electric guitar, and then which is wrong in any way. But then if the system shows that, okay, so this part of the image made me believe that it's an electric guitar, so you still kind of believe that the system is doing what a human would think, right? So if you show this part of the image to a human and then ask if it's an electric guitar, he would probably say yes, because maybe he will say I don't know or something. But then it's not really wrong that if the system shows this part of the image and says it's an electric guitar, it's probably doing okay. Okay, so let's take another different task. In this case, it's that of a visual question answering. So you'll be shown an image and then you'll be asked a question. So like in this case, this image is shown over here. And the question is, how symmetrical are the white bricks on either side of the building? So if you look into, this part, I don't know if my mouse is visible or not, but if you see this part of the building, so these are the white bricks that it's talking about. And it seems to be quite symmetrical to us. But the purpose here is to see, if you develop a system like this, and in this case, the prediction is, I think one single category here. So they had like, I don't know, 4 or 5 different categories. Like if you agree, or if you very agree with something, if you strongly agree, or if you agree, if you strongly disagree or disagree, right? So there are like this 4, or if you're neutral. So there were 5 classes of predictions in this case. So in this case, the system comes up with the answer that, okay, so I strongly agree with that it's symmetrical. But then you kind of, you are not really sure, because this is a complex question, right? And this is a complex image, where you are talking about a very specific part of the image. And then, if you have a doubt that is the system really understanding, so, it's quite easy to randomly guess. And if you have 5 options, then even for humans, if you randomly guess, even if you don't understand the question at all, you can randomly guess and still get it correct, right? So if there are 5 choices, then with probability of 1/5, you will get it correct. So probably these kind of doubts can come up in your mind, right? And then you need to be kind of looking at that, is the model really understanding the question? So, one way of explanation could be attention weights on the terms in the question itself, right? And maybe something like, graying out or highlighting some of the portions of the images as well. So in this case, explanations could be twofold, right? So since it's it's involving two kinds of data, one for the text and one for the image. So you could have both, right? So you could highlight the terms from the question itself, just to say that, okay, so these are the terms in the question that I think I should put more attention on. And these are the regions in the images that I think I should put more attention on, because that really correlates with the question. But in this case, if you see the explanation, it's not really a good one, because it puts more emphasis on terms like how. So in this case, red is the high emphasis, and blue is the negative emphasis. So it's really low emphasis, right? So imagine that it's between -1 and +1. So red will be the values that are close to 1, and blue will be the values that will be close to -1, and gray will be the values that will be kind of close to 0. So in this case, to a human, the words symmetrical and white bricks, they'll be the ones that will be more crucial, right? But clearly, the system puts how is not, it's not really important in this case. Maybe bricks, it has got some importance on bricks. White, it has got low importance because it's bluish. Either, it has got bluish, but either is very important, right? So it says that it has to be symmetrical on both sides. So maybe, you should put more emphasis on the word either, or either side, so as to say. But yeah, I mean, so if you look at this prediction output, then you know that, okay, the system is not really doing great. I mean, it might come up with the correct answer, but it's not really kind of understanding the question. Okay. So this is a different domain, which is called knowledge-based completion, or KBC for short. So in KBC, it's typically used to answer factoid questions. And then, you have a database of tuples. The tuples, they have 3 different types of entities or objects. So you have a head entity, or the subject, a relation, and a tail entity. So an example is that Donald Trump was or is the president of United States, or currently Joe Biden is president of the United States. So Joe Biden will be the head entity or the subject, president of will be the relation, and United States will be the object or the tail entity. So you'll have triples of this kind. And so, with many different triples, so maybe, it's not possible to have all the relations hard-coded, right? So you could have relations like president of, and you could have relations like married to, but maybe, you don't have a relation like the first lady of US. So you have to infer that, being a first lady is that, it's really, 2 different relations that you need to satisfy. You need to satisfy that you are married to the president, or you are married to a person, and that person is the president of US, right? So only satisfying these 2 criteria will qualify you to be a first lady of the United States. So the thing is, so although we don't have explicitly these relations, but still, to answer a question like who is the first lady of US, knowledge-based completion systems, they try to automatically infer these links between the entities. So they'll try to figure out that, okay, so maybe initially or previously, Melania Trump was the first lady of US, but then the system will figure out that, okay, so Donald Trump is no longer the president of US, Joe Biden is president of US, so we need to be kind of, modifying the link. So the link, as I show in this example, the link between Donald Trump and president has been cut off. But the first lady link still exists. So the knowledge-based completion system, will kind of figure out that, okay, so this is not correct, and it will automatically, remove that link and put the link in the correct place. So between Jill Biden and US. So imagine that if you have a system like this, and then, if it's a link prediction task that you answer, or you ask a question like, let's say for this example, right? Like who is the first lady of US? So in this case, want to predict the link between the 2 entities, and you want to also predict the type of the link. So type of the link will be, in this case, first lady. So if you just provide an answer, or if you provide with a probability that, okay, so with probability 0.9, I believe that Jill Biden is the first lady of US. But then probably you need to explain, and the explanation in this case is very different from the explanations that you have seen for text and for images, or for both. Because in this case, the explanations should be a path, right? So it should be saying that, okay, so there has to be a rule like, this relation is satisfied because I've seen all those relations. So if you provide an example, like Jill is the first lady because Jill is the spouse of Joe and Joe is the president of the United States. So that probably, will be a good expansion in this case. Okay. Then we can move on to something called counterfactual explanations. So the thing here is like, maybe, in this case, you have to, so I was giving an example of the doctors, right? So doctors, will have their own way of testing systems. So maybe, they will provide an additional symptom or, leave something out and then try to see, what does the model behave. So this is exactly what's done in counterfactual explanations. So, we will generate, or the system will generate in explanations in the form that, okay, so if that was your input, if this particular piece of information was not there, then my prediction would have been this one. If this particular region of the image wouldn't have been there, then I would have predicted this, or something of that sort. Or if this term in that sentence was present, then my prediction would have been different, which is very easy to see, right? So if you insert a not in a sentence, your classification should change, right? If it's sentiment classification system, you say that I liked that restaurant, but then if you add the word I did not like that restaurant, so adding the words did and not, will completely change the classifier. It should change the classifier output. So this is what is called counterfactual explanations, where you kind of explain the system by saying that, okay, so if things had been different, then my predictions would have been different. And this kind of gives a visual tool to the user, to the end user, who can kind of cross-check. Okay, so okay, that makes sense. So if this hasn't been there, so the system would have predicted this, which is quite the way we humans perceive, how we think about our decisions, right? So this is a way of cross-checking as well. So it has got particular applications in two different domains. I think one for policymaking, where you have many different options, and then you'd want to try out many different things. And so coming up with counterfactual explanations can really help. Say for example, if government wants to decide that if it wants to increase college education costs, it might want to see what would typically happen if I increase college education costs. And then and this is also useful for movie recommendation, when you see a recommendation and you want to know why am I being shown this recommendation. And a very possible explanation is like, say for example, in this example, maybe if you're recommended Scarface because if the system says that because you watched Godfather and Irishman in the last week, then it makes sense. But then if it says, if the system automatically says, you're not asking me, the system automatically says that, okay, if you hadn't watched Irishman, then I would have suggested Godfather 2, which makes you trust system more, right? So you are more convinced about the system or the original recommendation that it makes. So it kind of starts making more sense because you feel the connection. Okay, so Scarface, because I have watched Godfather and Irishman, so they are both similar types of movies, and hence I am suggested this one, which is making sense. So one thing that I want to tell you at this point is that this is difficult to kind of implement for all possible or all different domains, right? So let's say, for example, text. What will you leave out and what will you include? There are many different options. And then, so this is often a challenge, a very difficult challenge to solve in counterfactual explanations. Because, if you look at this point, X, so you want to explain this point, but then you need to be kind of moving on to different points, corresponding to the fact that, if things would have worked differently. So you can move on to many different points, right? So in the neighborhood, there is an infinite number of points that you can choose, but which one will you choose? It's difficult to decide. So in this case, if you look at the true data distribution, that's being shown by the data manifold here. So it makes more sense to choose B because B is close to the manifold, but A is further away from the manifold, right? But the distance from X to B is higher than the distance from X to A. So there's this trade-off, right? So you want to choose points that are close to you, because that's how, if the point that you sample or if the point that you generate is very different from your initial point, then probably it's difficult to see the connection, right? So that's why, if you choose B, maybe it's difficult for humans to visualize that, okay, so, B is too different from X, and I'm not being able to make that connection. But then B is a representative of the data that you might see, and A is further away from that. So it's very less likely that you will see something like A in real world. So these are the difficult things that you should be keeping in mind, when dealing with counterfactual explanations. Okay. Yeah. So as I was saying that, okay, so let me actually move on to some of the characteristics of the explanation models that typically. So I'm not talking about any algorithm in particular, but about any explanation algorithm. So it should really be interpretable. Like, it should be giving an explanation in very basic units. So we have seen examples of those kind, right? So in images, we have seen that these are regions for images. For text, we have seen that these are words or phrases. For knowledge-based completion, we have seen that they are paths in the graph, knowledge graph. So they should be very basic explanation units that we humans should understand, right? So they should be as atomic as possible or as fundamental as possible. And then, there has to be some element of local fidelity. So which means that, if I am trying to, explain an instance, or if I'm trying to, or if the model, is suggesting a class for a particular instance, it's coming up with a prediction, a predicted class for that instance, for similar points, it should kind of come up with the same category, right? I mean, if you show, let's take the example of, I don't know, a cat versus dog classifier. So given the image of a dog, I mean, if you show similar images of dogs, maybe with the same color or with the same breed, it should come up with the same class dog. I mean, if it comes up with a different class cat for a very similar image, then you know that the system is not really working well. So obviously, you could test that with a test set, but test set is not comprehensive, right? So, a way to check if the model is consistent, not accurate, but consistent, is that, if you provide slightly different inputs, maybe a doctor, will add some symptom or remove some symptom. So in that case, your prediction could be a lot different. But for some domains, changing very little, would not really cause a very great change in the predicted class. So that's something that we need to also check. So trustable systems or systems that we can trust, they involve some kind of local fidelity as well. And obviously it has to be model agnostic, right? I mean, your explanation mechanism, can't really depend on the internal working principle of the model that you want to explain. Otherwise, you will have this vicious cycle, right? I mean, so on one hand, you are trying to explain the model, it could be, an LSTM, or it could be a convolutional neural network. But if your explanation mechanism also depends on whether it's an LSTM or whether it's a convolutional neural network, then how do you even trust that explainer, right? I mean, it's kind of explaining its model, or explaining its underlying model with the help of the model itself. So you don't really trust that thing, right? I mean, so it has to be as much as model agnostic as possible, because otherwise you won't trust that internal working model itself. Otherwise, and also one of the reasons is that if it's not model agnostic, then you need to be kind of developing algorithms for every different model that you build up, right? So it's not really possible. So that's why it should work by just taking into account the input and outputs that you supply to the model. Okay. So I'll talk briefly about how it works, or how the explanation works. So you'll be given one particular instance that you want to explain, and that's why it's talking about the instance-wise explanations. So take one particular instance, which is some fixed dimensional or dense vector of d dimension. And given a particular data instance and a parameter, so you already have a model that's trained on this data set, right? So you know that you have trained a model that you want to explain that can classify the label y, given that x. So you have that model trained, theta. Now, all you need to do is to sample points that are close to x. So we denote that with a neighborhood function. So you take a point z that belongs to neighborhood of x. We will see different ways of sampling. So one of the ways to sample is to take points. So you can have your training set, and then you could take points that are near to the point x. That's one way of sampling. The other way of sampling would be to leave out some units from your data. So if it's text, you could leave out some words or insert some other words. And if it's images, you could leave out some regions from the images. And then, once you obtain this neighboring point or the set of neighboring points, you try to fit a simple classifier on this subset of instances. So your whole model was trained on this, maybe, tens of thousands or even hundreds of thousands of points. But when you want to explain one particular instance, you typically will take a very small number of points in the neighborhood, maybe about 50 or something. So here is a visual example of how it works. So this example is taken from Lime, but this is the same principle by which every other expansion mechanism will also work. So this has got nothing Lime specific. This is also how L2X and Shapley will work. So the thing is, so in this case, you want to explain this red cross. So that's your current instance that you want to explain. And you need to sample points from around this point. So in this case, you sample points which are either this small sized brown crosses and these ones as well. The size of the points in this case determine the weights that you are putting on each of these. So this is Lime specific. So Lime actually puts more emphasis on the points that are closer to your instance. And then, once you take these set of points, you typically fit a very simple classifier, in this case, a line. And then, if you fit a linear regression like this, it's possible to, have an idea about the weights of the classifier line that you fit in. And these weights, they will serve as your expansion units. So in this case, you basically are trying to transform x, which was your initial point, into, a simple representation phi of x, which involves a lot less number of parameters, which could serve as a expansion unit. So basically, you minimize a loss function like this, right? So you take points. So this loss function depends on that instance x that you want to explain. So that's why, you have x here. You have theta as well, because theta is the trained model that you want to explain. And phi is a learnable set of parameters for the explainer model. So, in this case, you start with phi's and then you update the phi's based on that propagation. So the loss function that you want to minimize is that you sample points in the neighborhood. So you have the summation over the neighborhood points. So you take the model prediction, right? So you apply theta of z. So maybe, theta of z. So for this example, okay, so for this example, so this is red, right? So theta of z in this case is a red cross. It might have been the case that, this had been a blue dot, then expansions would have been different. So theta of z is really, it's not the true ground truth label, but it's the predicted label that's coming from the classifier, right? So which you want to explain. So theta z minus phi of z. So you're trying to fit this over this. So it's a simple linear regression equation that you want to solve, right? So instead of the ground truth values, you're just using the theta of z. And once you minimize the square loss, then you get the parameters for phi. And the neighborhood of x in this case, as I said, you could take points from your training set, or you could turn on or turn off some of the basic data units from your instance, right? So if you have got images, then you could turn on or turn off some pixels. Or if you have a notion that you could also work with regions of pixels rather than one single pixel. But the idea is like, you will sample random vectors and then you will mask, right? So you will turn on, some of the bits, not all of the ones. And then by turning on the bits, you can kind of ensure that, okay, so these points are exactly the ones that were there in X, but the ones that I leave out are zeros, but still the inner similarity or the cosine similarity between the two will be quite high. So Z will typically, be close to X. So that's something that you are guaranteeing, right? I mean, you can't set everything off, because if you set everything off to zero and just retain a few bits, a few ones, then your distance of Z from X will be quite high, which you can't do. So you have to ensure that you have a fair number of bonds, in this random bit vector, and only a handful of zeros. Okay. So as I said, like, so your expressions will be different depending on the class in which you are predicting, or depending on the exact class into which the prediction system is classifying your image into. So, sorry. So in this case, you had an image of this complex image involving many different elements. And the system says that, okay, I believe it's an electric guitar, with this probability, and I believe it's an acoustic guitar with this probability, and I believe it's a Labrador with this probability. And you want to explain each of these predictions, right? So in this case, your predictions will be different, or your explanation units will be different, because if you see this equation, right? So it depends on the theta of Z. So theta of Z, in this case, there are three different theta of Z's. So in this case, you're predicting, electric guitar. So let's say that's Y is equal to 1. In this case, let's say acoustic guitar, so Y is equal to 2. And in this case, Labrador, let's say Y equal to 0. So you have got, let's say it's a softmax of three different probabilities. And, so depending on, what you are predicting, your outputs will be different, or your phi values will be different, right? So you will learn different sets of phi's for each of these outputs, or for each of these instances. But then you should try to kind of see that, okay, so depending on my predicted class, if the system comes up with the features on which it puts more emphasis on, does that make sense? In this case, it does, because as I said with this example, the electric guitar, if you just look at this part of the image, then you believe that it's an electric guitar. If it's an acoustic guitar, then probably this big part of the guitar, putting emphasis on this part, that makes sense. And if it's a Labrador, it's a dog, then this part. If it was a man wearing a shirt, then probably this part would have made sense. Okay, so that's the basic takeaway. So I don't want to be delving into more details about the algorithms themselves. But let's so I talked briefly about the instance-wise explanations and the model-wise explanations. So model-wise explanations, as I said, are difficult to do, because it's not really clear, from the individual instances, how would you actually build up, a whole modelable prediction. But one way of doing that is to apply something like a greedy set cover. So you sample instances, and then you look into the feature importances, right? So let's say you have a training set of, I don't know, images or of documents. Then you could sample instances, and then you could see that, okay, so this image, I have got these objects. This image, I've got these different objects, right? So there's no point of taking, similar images and then explain the model. Whereas you should be taking quite distinct data elements, right? So in this case, if it's a classifier system about dogs or anything else, then maybe, if you take an image like this, then probably there is no point of taking another image exactly like this. So maybe you should take another image like a dog playing in a ground or something. So that would give that would mean that the explanation units that you come up with will be very different, right? So in this case, it's a guitar part, or it's a dog's face. But maybe if it's a dog playing on a green field, maybe then you come up with other elements that we haven't seen before. So in that case, or in that way, if you come up with importances of features, then you could choose a subset of instances, which gives you the maximum coverage, right? So in this case, if you do the analysis, and then come up with feature importances. So let's say, this one, it has got F2 and F3 high, and this one has got F4 and F5 high as well. So if you take these two, we kind of cover all the features, right? So you should be trying to cover as many features as possible with as small a number of instances as possible. So this problem as such is NP-complete because it's a set cover problem, but there are greedy solutions to it, right? So you could just apply the greedy approach and then take the instances which kind of approximately cover the entire set of features. And the good thing with the greedy approaches is that you have polynomial time approximation solutions for this. I mean, it's guaranteed that the set that you end up with will be at most twice the optimal set. So there are bounds like this, and then the greedy solution could work. But this is still, I think, an open area of research, where moving from per instance explanations to model explanations is not really that simple. Okay, now let's move on to some of the future thoughts about what do we want to achieve with these explanations. I mean, all this is fine. So we have seen instances where you show one instance and then you see either you see some weights of the words or of the pixels, and then you kind of try to make sense of the predictions. But these are very simple prediction systems, right? So it just takes an input and then comes up with an output. And for very, very particular domains. But then that's not how, we envision intelligence. I mean, intelligence is something, where you'll be able to make decisions in unforeseen situations. I mean, that's a true measure of intelligence. It's not like, mugging up that this is how a cat looks like and this is how a dog looks like, and then, given very similar images, I'll be kind of predicting. It's not a sign of intelligence. So intelligence, as I said, it's a continuous process because you have to take decisions at every step, and you may not have a complete picture of the entire world at every step. So at every step, you have to intelligently choose your action. So that's typically how reinforcement learning works, because you don't have a complete picture of the environment initially. These abstractions that we were talking about, I mean, so maybe, you need to change your abstractions, right? I mean, like for cats and dogs, if you want to classify between puppies and kittens, or between puppies and cats, or between dogs and puppies, then probably, you need to kind of move back and forth between the abstractions. So that's a true sign of intelligence. So I'll give an example. So this is by the Russian computer scientist Bongard, Mikhail Bongard. I don't know if I pronounced his name correctly. I'm not Russian. So this was invented by him, as tests or computation tests for pattern recognition for computer systems. So this was done way back in the 60s. But then it was popularized by the famous book, Gödel, and Buck by Douglas Hofstadter. So I'll try to explain, what the problem is about. So in this case, you'll be having two sets of images, one on the left and one on the right. And you need to explain that, why the images on the left are different from those on the right. So you won't be given any information, right? So you've just shown, these two sets of images. So obviously, you need to kind of build up abstractions and then kind of figure out mainly three different things. So one, why are the images on the left-hand side in the same cluster, in the same group? So what are the attributes that's common, between the images on the left? And you have to do the same for the right. So what are the attributes that are common for the images on the right as well? And they have to be consistent, right? So images on the left, I mean, if you see one image that's not exactly fitting your description, then probably it doesn't fit in, right? So if you look into this particular set of figures here, and if you assign the attribute black, that all the images should, so you can start with something, right? So let's say that you think in your head that, okay, all the images here should be black. But that's not really the case, right? I mean, you have white figures here as well. I mean, the inside of these figures is colored white, but these ones are black. So you may say, okay, so maybe, I put in this one and then put in this one here. Does that help? No, it doesn't, right? Um, because, it's clearly given that, these two are different sets. So you need to kind of finding why is that the case. So that doesn't work. Then what works? So you need to be kind of saying, okay, so if you count that if it's a triangle, no, everything is not a triangle. I mean, you have a circle here as well. I mean, so you don't have like curvy, it's not the case that you don't have curvy figures on the left-hand side. You do have circles. So what could be the reason? So I'll show you the reason, but then let's see, how we can think about it meanwhile. And then, if you think about, okay, so I was talking about the fact that, okay, so you need to build up these notions that, okay, so there has to be some similarities between the figures on the left and some similarities on the figures between the right. And you also have to figure out, why are these two sets distinct, right? So on one hand, you need to compute or you need to build notions of similarities. And on the other hand, you need to build notions about dissimilarities. And, they have to be consistent together. So this is not a simple task, right? So this is quite different, quite difficult task, because you need to be kind of moving back and forth between the different levels of representation that you may need. So this was a simple example. Probably you already have figured out why are these two different. But then let's talk about this set of figures here. So in this case, we have, I don't know, it looks very similar figures. I mean, in this case, clearly, you could see that, okay, so this is a black one and, but in this case, all the figures on the left, they're also on the right. So what makes them different? So can you think about an answer? So the answer in this case, I'll tell you the answer. So in this case, the attribute that you should really think of is the size of the figures, right? So it's not the shapes that matter, but it's the size that matters, right? So the size is clearly different. So you all have small figures on the right, and you have big figures on the left. So size in this case is a discriminating factor that you should take in, or you should consider to be kind of distinguishing between them. And in this case, you have small figures present on the images in the left, but you don't have small figures. Although the figures are exactly of the same shape, but again, size is the one that matters. So color doesn't matter here. Color, there is no question of color on the right hand side. So you need to kind of thinking about what kind of features you should consider. So some problems, so those two problems were kind of easy one-word problems, but then you could land up with more difficult problems, where you need to really think, maybe for hours. So you need to be building features like, as I said, features could be simple or it could be complex as well, like number of corners, lines. They're simple features, but other features like convexity, they could be, very, very abstract features that you need to build up. So in this case, it's a really difficult problem, because if you see that the images on the left, if you think about in terms of the shapes or maybe indentations or something else, then you can't really figure out, why the set on the left is different from the set on the right. You might think about convexity, but it doesn't really work. But the key here is to see that, okay, so there is the abstract notion of the number 3 that's represented by these images. So you have got 3 sides. You have got 3 sides in the triangle as well. You have got 3 figures. You have got 3 indents in this shape. You have got 3 dots in this shape. And in this case, it's 4, right? So you have got 4 sides. You have got 4 outdents. You have got 4 crossings. So, it's unless you build up that abstract notion of 3 or 4, you can't really, explain that why are the two sets different. And the same here. I mean, in this case, it's not the number, but it's the density. So the density of the points in the interior of this, it's quite densely packed, right? But then here, they are not that densely packed. They're kind of spread out. But then that only applies for the points on the inside. So concepts of inside and outside, concepts of density, concept of number in the abstractions, these are the ones that you should really build up in your head to be able to justify that why are the two sets different. So the current explanation state of the art that we have, we have attention weights over images, right? So we have images in this case. So we could come up with attention weights and try to explain our answers, but that doesn't really work, right? So, if you consider this example again, so in this case, so you have got small figures on the left, but then you don't have small figures on the right. So maybe in this case, it does work a bit because you are really pointing to these parts of the images and then saying that, okay, so that's why I think this is different. So maybe in this case it works. It doesn't work for this particular example, right? I mean, it's all scattered around. I mean, in this case, you can't really see that why are the two figures different. So the answer in this case is that you have got indents or inward moving angles on the left side, but you don't have the inward angles on the right side. And if you look into the explanation, it's nothing close to, it's nowhere close to the explanation that we can build up in our minds, right? So as I said, right, so rather than just showing a heat map on the very basic, at the very basic fundamental level of pixels or words, we should be kind of providing natural language explanations, maybe at different levels of abstraction. So this is where, I think that we should be moving ahead, in the coming future, so that, we can apply explanations, not just to very simple classification problems, but we can apply it for reinforcement learning, and we can apply it for, this unseen or unsupervised notions of learning to test the real comprehension about, how systems work. Okay. I won't take much of your time, but I will just quickly browse through this part. So I was talking about building these abstractions in the models, that the abstractions that the models should build should be quite similar to what we humans do. But the one risk is that, if you are building abstractions like this, you could suffer from cognitive biases from which humans have suffered, maybe in the last decade or something. But then situations are improving now, and then, humans are kind of, society is becoming more liberal, and we are kind of, getting over these prejudices that, we once formed. So getting rid of the cognitive biases, is a critical challenge. And, these abstractions that the systems are building, I was showing this example, I was setting the example of the brown skin color to determine, if it's terrorist or not, or if it's a criminal or not. So skin color is not definitely, something that you want to leave out. So if you look into the abstractions and then kind of figure out that the way the system perceives or the way the system builds up the abstraction from the data, the skin color emerges out to be one of the crucial factors that can affect the decision, then that's not something that we want, because we want a fair system, right? So explanations like this, where you show the different weights to the different components in your data, could be helpful to build more fair systems. So that's something that we can do. So it's also got societal applications, where you could kind of build more fair systems. So I think I'll stop here, and then so I'll just provide a summary, and then we have 2 follow-up talks after this as well. So we have briefly seen the explanations in AI, and it's a medium to build trustworthiness with end users, and it's a tool for practitioners as well to develop more effective models. But as I said, it's a tip of the iceberg, right? The current state of the explanation, it provides explanations in terms of very basic units, very fine-grained units, which is not really something that will be useful in the future, because it lacks the true test of comprehension, right? So we need to be coming up with explanations that are more easy to understand, maybe spanning across different levels of abstraction, and as I said, maybe apply for different classification tasks, both unsupervised and semi-supervised, and maybe reinforcement learning settings as well. So please stay tuned for the 2 talks, and I'm prepared to take any questions. So I don't know how much time do I have for the questions, but please feel free to ask any that you might have. Thank you. Hello. Hello.
Yes, sir. We don't have any question at the moment.
Okay.
So,
Yeah, I mean, whenever you have a question, I mean, if the audience has a question, then I'm here anyway, so I'll be answering that. I don't know. So maybe, we can wait till the next talk, and then, we can have a Q&A session, so let the audience think for a while. And then after the three talks, we could all be there to answer questions if there are any. Does that work for you?
One
yes.
quick question, sir.
Yes.
So it was definitely wonderful session to learn more about explainability, because if we just make it as a black box, then a lot of things are actually hidden from the end users. So uh,
Mhm.
yeah, it's definitely helpful. But as you said towards the end of your talk about the abstraction part, so how
Mhm.
do we actually build a balance between uh, natural language explanation versus the level of abstraction? So
Yeah, that's a very difficult task to do, right? And it will take years of research to do that. So it's like, I don't know, it will take a full PhD student to work on that problem and then figure out how to do that. Because, it involves different parts, right? So it involves firstly to correlate between text and images in the first place. Because even if you take the Bongard problem is just, one simple, way to illustrate this. But even if you take the Bongard problem, you have to kind of correlate between the image features and between the text features, right? And it's very difficult to express the abstraction, that the model builds. I mean, yeah, I mean, you could have attention weights is the most obvious way of doing that for very simple units. But then it's very difficult to see, how do you actually correlate the abstractions that the model builds into the real features that we humans perceive. So there is no clear mapping like that, right? So, trying to obtain some kind of an estimate of the correlations, is something that's also very challenging. So multimodality is definitely one challenge. Then, mapping between the very basic units and between the abstractions that we humans perceive, it's also difficult. So I don't have an answer to the question. It will take years of research. I need to put in some more thought to it as well. Maybe write a proposal and then make some students work on that. So yeah, it's
yeah,
it's it's not it's not it's not something that I can answer right now, but it will take years of research.
right, sir. So basically, there should be some best practices that are domain specific, or maybe when you said when we move from feature driven to data driven. So
Mhm.
I mean, there are a lot of macroeconomic variables and a lot of other features that come into play. I mean, taking into example the corona and a lot of other variables that actually uh, drive the markets, right? So
Mhm.
I mean, the data keeps changing, consumer behavior keeps changing. So basically, I mean, it's really difficult as to say, but if there could be some best practices as to how we can explain model outputs in a more human understandable form,
No, if the
maybe.
data changes, then so the good thing about data-driven models is that all you need to provide is the examples, right? So you need to have annotations for those data. I mean, if data changes, then if you provide annotations to the new data, then you can apply existing models to work on those new kind of data, right? And so your explanations will definitely be different. But then the good point is that your explanation algorithm doesn't need to change. Your machine learning model doesn't need to change. Although your application domain is changing, like say for example, the classifier between cats and dogs and between puppies and dogs. So puppies look quite different from cats. So and the granularity of classification is also different, right? So cats are very different from dogs, but puppies are not that different from dogs, right? So in this case, all you need to do, if you want to build a new classifier, is that you need to provide new labeled examples that these are puppies and you already had images for dogs, right? So it's a new classification that you want to make. But then you can apply the same, let's say the Lime or the L2X or Shapley, on those new models as well. And maybe you'll get different attention weights for your new domain, right? So maybe, for cats, the images were looking in the whiskers. I mean, although you don't mention that explicitly as a part of your feature, but maybe it turns out that with lots and lots of examples, it has somehow figured out that the presence of whiskers in that part of the image, maybe, that's a crucial factor that determines that it's a cat. But maybe it's a different explanation unit for puppies. But you don't need to work on that explicitly, right? So you don't change the algorithm itself, or you don't change the explanation mechanism itself. It all works. So even if your data changes as per your, market economy or commercial factors that might be driving towards a different kind of classification, a different kind of prediction task, from a good thing is that from the model point of view, everything remains the same. And we need to, retrain the systems and then, retrain the explanation system as well to get results. I don't know, does it answer your question, or I misunderstood your question completely?
Yeah, that helps a lot, sir. So, I mean, I was mostly looking from traditional classification problems, something like a
Okay.
financial
So yeah,
statement or
okay. So
something
this
like
is
that. So,
yeah. So
something
a
that
good
gets.
point. Yeah, so a good point with the explanation mechanism is that, although I presented it in a way like, it's more true for data-driven models, but it also works for feature-driven models, right? So, but for feature-driven models, it's even easier. So, techniques like Lime or Shapley, they will give you feature importances for each discrete features that you might have. So if you have a CSV file, if you have relational data, right? So you have, I don't know, 100 different features for every instance. So if you throw that to Lime or Shapley, you will get the most crucial features depending on your classification task. And depending on that, you could leave out some features, or, you could, I don't know, do something else that suits your task. So it's also possible to apply it for feature-driven models as well.
Okay.
But for feature-driven models, I think, we humans already do have an understanding of how things work. But then, as you said, that for critical domains, maybe, we as machine learning engineers, we may not have an idea about, what are the important features. Let's say for the market economy, I don't have a clue about what features are important. But then that's something that, you can discover from the data. So techniques like Lime and Shapley will be able to give you the feature importances as well.
Okay, got it, sir. So basically, using Lime and Shapley, we will get the correlation with multiple features, and that's how we can actually.
I mean, so it's really easy for feature-based systems, right? So you could easily compute something like, mutual correlation between features, and I don't know, there are lots and lots of techniques, from the 60s. You have something called the influence functions, and then there are very many different things that you can do. Even with linear regression, it will give you, the coefficients will give you the importance of the features, right? So, yeah, that's easier to do for feature-based models. Yeah,
got it. Thank you, sir.
So unless we have further questions, then I think the next speaker can start her talk. So the next talk will be by Pochita Shen, and she'll be talking about learning to explain model L2X. By the way, I think we can take a small break of 5 minutes, right? Is that something that you want?
Yes, sir. Or can we take a lunch break?
Oh, yeah. It's lunchtime, right? I forgot about it
Yes, sir.
completely. So yeah. So at what time do you want to come back?
So we can join back at 3 p.m. if you agree.
Which is half an hour from now, or how
1.5 hours.
1.5 hours. That's
Yeah.
really great. Okay. So we'll be meeting after 1.5 hours. Okay, that's fine.
Yes, sir. Thank
So
you
in
so
the
much, sir.
yeah. So in the meanwhile, I mean, do you have any further questions for my talk, or? If no, then we can join back after 1.5 hours. That's fine. Thank you then.
Thank you so much, sir, for such a wonderful session. I'm sure everybody found it to be very enlightening, and hope to see you soon, sir, in the
Thank
next
you.
session.